Okay, we have some blanks to fill in. Here, you're going to write the word real. Here, that's positive integers. Sorry, it kind of looks like t integers. It's positive integers. Here, you're going to fill in roots. Here, zeros. Here, factors. Roots, zeros, factors. You can write skip over all this because we're going to get to that later. And now guided practice. Truly, y'all have already been given a preview of this. Y'all started working on this on our last Delta Math assignment, but now we're like, okay, now let's actually go over it. Here, for all of this, what they want you to just be able to do is look at the function and tell whether or not it's a polynomial function or not. Now, example one, that is an example of a polynomial because all of our exponents are positive and none of our variables are being square rooted. But yeah, that's a polynomial. But before we get going, let's see if we remember some things from last class. Can you tell me what degree polynomial this is? Fourth. Very good. You're ahead of me. Fantastic, Sammy. I was about to then ask you, what's the name of a fourth degree? Sammy already did it. Quartic. Fantastic. Since it's a fourth degree polynomial, is your end behavior same or opposite? Same. Even, same. Either up, up, or down, down. Which is it in this case? Up, up, or down, down? It is up, up. The way that you can tell is, well, we've already established this since it's an even polynomial. It's either up, up, or down, down. To figure out which one is it, look at the leading coefficient. The fraction doesn't matter. The fact that it's positive does. And since it's positive, then our end behavior must be up, up. All things you're going to need to know by Tuesday. Okay, this one, not a function. Why? Because if we distributed this 1/2 throughout the parentheses, we'd be square rooting everything, including the x. And the square root of x is not a polynomial function. This one, no, because we're dealing with a negative exponent. This one, yes, linear. This one, no, because your exponent happens to be a variable. And this one, yes. Move on to side two. Yes. Wonderful question. What is the difference between 2 and 5? Well, the difference between two, thank you, sir. The difference between two is we're raising everything in the parentheses to the 1/2 power, including the x. And anything raised to the 1/2 power is the square root. You can't take the square root of x and it be a polynomial function. Here, they're just raising 7 to the 1/2 power. You can have the square root of 7 and it'd be a polynomial function, but not x. Wonderful question. In fact, I think we should just end notes for today. We're not going to get a better question than that. Everybody go ahead. I'm kidding. Please fill in these blanks. All right, here's the blanks that you're filling in. To find the zeros of a polynomial function, you can factor, use the quadratic equation, or synthetic division, or long polynomial division, truly. There could be more blanks here, but I think 3 is enough. Dang it. Time out, everybody. What were we on? This one. Okay. Now let's start. I can't believe I get paid to talk for a living. Okay. Example one. Given this particular polynomial, it's a polynomial because we know there's 1, 2, 3, 4 terms, polynomial. Find the zeros, find the x-intercepts. And then we see semicolon, and then x minus 1 is a factor. That is almost always a dead giveaway that you're going to have to use synthetic division or long polynomial to solve it. Synthetic is easier. If you're going to use synthetic division, take x minus 1, set it equal to 0, and solve, which would give you 1. So we're going to divide this by 1. Hey, for those of you that are going to retest today, like the first 3 problems, pay attention. I mean, I encourage you to pay attention like all the time, but you really want to pay attention now. You'll probably be seeing this again soon. All right, 2x cubed. All right, our synthetic division is set up. In the event you don't remember how to do this, let's do it. Whatever this first number is, bring it down, don't change it. And now we multiply. 2 times 1 is 2. And now we add 5 plus 2, 7. And now we multiply. 7 times 1, 7. Add -4 plus 7 is 3. Bring it on down. Multiply. 3 times 1 is 3. We've reached the end, and -3 plus 3 is 0. No remainder. Next, bring down your variables and decrease by 1 exponent. Hey, those are positive numbers, so let's put a plus there and there. In order to continue working this problem, to find the zeros, to find the x-intercepts, we now need to factor this. So I'm going to go a little bit faster now because we've been factoring for a very long time. 2 times 3 is 6. 1 times 6 is 6, and 1 plus 6 is 7, positive 7. We have our factors. You have to create a grouping problem. Group 1, group 2. At a group 1, we can factor out a x, leaving you with 2x plus 1. Group 2, you can factor out a positive 3, leaving us with 2x plus 1 again. Now that we have factored, you take each of these and set them equal to 0 and solve. And if you did that, here you'd get -3. Here, you would have to subtract 1, divide 2. We have now found the zeros. We have now found the x-intercepts. They're the same thing in this case. So -3, -1/2, and I'm missing 1. You know what it is? 1! The number that we use to do synthetic division. And here you can put same, because our x-intercepts are the same as these zeros. Y-intercept. This is written in standard form, therefore it's the constant. 0, -3. Example 2. Those of you that are needing to read fast, I pay attention. Looking at example 2, we can start by factoring out an x squared. Leaving us with that. If you take away x squared from all of them, essentially dividing the problem by x squared, that's what we're left with. Now we have a trinomial inside the parentheses. 1 times 4 is 4. These are the factors that we have to use. -1 times -4 is 4, and -1 plus -4 is -5. Your leading coefficient, 1. So we're going to save ourselves some time. Let's see who remembers. Am I correct? No, what am I missing? Okay, you're on the right track. Good. These need to be squared. If this was x squared minus 5x, then my original answer would have been correct. But if it's ever x to the 4th, make sure you square these. And then, as you mentioned, now that I've written it correctly, I have a difference of squares problem. Now it's fully factored. And we can begin to answer the question. Our zeros are, what is it here? 1. What is it here? -1. Here? -2. Yeah, okay, so I'm going to write ±1, ±2. Don't forget, in the front of our parentheses, we have x squared, which you're also supposed to set equal to 0 and solve. To eliminate the square, square root both sides, and the square root of 0 is 0. So that's our other one. Those also happen to be our x-intercepts. You could write same y-intercept. This is written in standard form. There is no constant, 0, 0. Move on to the next side when you're done with that. If you have stuff written in factored form, there's shortcuts that you can use to fill in all this information. But let me tell you what you're going to have to know to do, which, by the way, we've already covered in this class up to this point. You're going to need to know how to multiply all that. FOIL it, box method, whatever you want to call it. You're going to need to know how to do that, but it takes a long amount of time. So I'm going to show you some shortcuts to help lessen it. Degree, roots. Here's what you're going to do in this example. To figure out the degree, take whatever the leading terms are in each parenthesis, multiply them. So x times 2x is 2x cubed. Here's what we now know. We now know that this is a third degree polynomial with a positive leading coefficient. So third degree, which by the way is a cubic function, zeros. This is already written in factored form. If x minus 2 is a factor, then one of the x-intercepts must be 2. Or one of the zeros. Here, if it's x plus 3 is a factor, then one of the zeros must be negative 3. And then here, if you subtract 1, divide 2, subtract 1, divide 2, we now have the other one. Here's how you can quickly identify your y-intercepts without having to multiply all this together. Look at your constants. Negative 2, 3, and 1. Multiply them together. Negative 2 times 3 times 1, 0, negative 6. We have already established this is a third degree polynomial, so how many terms do we have maximum? 2, good. Our leading coefficient is positive 2. And now we can do in behavior. This is a odd degree polynomial. So our arrows are going to be going opposite direction, odd opposite. The leading coefficient is positive. So our arrows must be going down, up. All things we learned last class. So for this first blank, if this arrow is pointed down, let's do negative infinity here. And for this last blank, if that arrow is pointed up, we're going to do positive infinity here. And then you're going to have an idea of what this graph is going to look like. Because odds are in your next test, they're going to give you a function like this and then some graphs, and you're going to have to be able to match. And this is how you can do it. We've already established what our zeros are, our x-intercepts. We have an x-intercept at 2, negative 3, and negative 1/2, which is right about there. Our y-intercept, we can also plot that, is negative 6. So that's right about here. Our end behavior is up, down. No, it's not. It's down, up. My mistake. Down, up. Down, up. Third degree polynomial, 2 terms. So we're going to go through this point, turn around, go through those points here, turn around, go through that point there. So we're looking for the graph that looks something like that, if you happen to see something like this on your next test. Okay, we've already worked something similar to this. Let's go and take a look at example C. This one's a little bit different. With example C, here's something that you can do with this, is that it's not fully factored yet. Example C, this is a difference of perfect squares. That factors to x minus 1, x plus 1. Here, I'm going to do some quick factoring. This can also be factored, this trinomial. It would factor to x minus 3, x plus 2. See how many of those blanks you can fill in now. Don't worry about the graphing part. See if you can fill in everything else. Jump in here and start giving you some answers. Let's find the degree. Now that we factored it, to find the degree, look at the term in front of the parentheses. X times x times x times x is x to the fourth. So this is a fourth degree. We also now know the leading coefficient. It's positive 1. So let me go ahead and fill in those blanks. Fourth degree, which by the way is a quartic function. Our leading coefficient is 1. Zeros, now that they're all factored out, we can find them very easily. We have a 0 at 1, negative 1, 3, and negative 2. Plus or minus 1, 3, negative 2. To find y-intercept, now that we factored everything out, let's look at our constants in the parentheses. Negative 1 times 1 times negative 3 times 2. 6, looks like. 0,6. Maximum number of terms. Well, now that we've identified it's a fourth degree, 4 minus 1 is 3. End behavior. This is a even degree polynomial. So same direction. Up, up, or down, down. Your leading coefficient, good, is positive. So it's going to be up, 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 up. So both of these blanks need positive infinities. All right, up to this point, more or less, this is a review we've done so far this unit and previous units. We've been factoring for a while, and we went over end behavior and degrees and all that stuff last class. Let's take a look at some new information that we're going to be doing today. I think I can zoom in now. Probably could have. Oh, that's not any better. Okay. Here, write the word cut. Here, bounce. There, flatten. You're going to be introduced to a new word today. That word is called multiplicity. Multiplicity means in factored form, what are the exponents? This factor has a multiplicity of 1. This one has a multiplicity of 2. This one has a multiplicity of 3. Pretty easy so far, right? Squared, and that's multiplicity of 2. If it's cubed, that's multiplicity of 3. Now, based on the multiplicity, you should have an idea of what your graph is going to do when it gets to that x-intercept. So if we're going to graph this function, well, first of all, one of the things that we have to be aware of is what degree are we even dealing with? The long way is to do x plus 2 times x minus 1 times x minus 1 times x minus 3 times x minus 3 times x minus 3, and no one wants to do that. This is the fast way. This is factored. Look at the exponents of the factor. This is an exponent of 3. This is an exponent of 2. This is an exponent of 1. Add them together, we get 6. This is a 6th degree polynomial. Meaning our end behavior is same, up, or down, down. Because it's even. To find up, or down, down, remember, multiply the numbers in front of the parentheses. X times X times X, that's going to be positive. So we know our end behavior is going to be up, up. All right. This x-intercept is going to occur at -2. So I'm going to go left 2 and put it out there. Here, this x-intercept is going to occur at 1. So write 1, put a point there. This x-intercept here is going to occur at 3. Put it out there. And then now let's think about our y-intercept. Up to this point, you have been told, identify your constants and just multiply them. Well, that works if your multiplicity is 1. If you have multiplicity of 2 or 3, we got to do a little bit more math. So here, the constant is 2 times, here, the constant is -1, but we're squaring it. And -1 times -1 is +1. Here, the constant is -3, but we're cubing it. -3 times -3 times -3 is -27. Now multiply all those together, and we get -54. That's our y-intercept. Now, we don't have that big of a scale, so let's just say our y-intercept is going to be here. Now, here's where all this stuff comes in handy. At -2, let me draw my arrows really quickly. I know my end behavior is going to be up, up. At -2, our graph should cut through that x-intercept. So like this. Let me go and hit that y-intercept there. When we now approach +1 here, if it's squared, that means your graph is going to bounce at that point. Ricochet. Boom. And now, as we begin approaching the next intercept of +3, that means our graph is going to flatten out at that point. Oops, I missed my arrow. There. So how in the heck does this apply in the future? If I see this function and a bunch of multiple choice options where I have to match the function with the graph, I'm looking at, well, first of all, which graphs have an x-intercept at -2? And I go and I find which graphs have an x-intercept at -2. And then I find which of those graphs is my graph going through -2. Here, I then look at those graphs and say, which of them also have an x-intercept at +1? And if they have an x-intercept at +1, then it better be bouncing at that point. That's how you're gonna, this is how you're gonna take an equation and matching it with the graph easy, just by memorizing the multiplicity. This one here, when a polynomial has repeated factors, that root is set to have multiplicity. When a factor repeats 2 times double root, it will create a curve. Now, I've been using the word bounce. Yes, it will bounce. The more technical term is tangent. When a factor repeats 3 times triple root, it will flatten at the x-axis. And then here, what they wanted you to do is just have some sort of an idea of what this could look like. Here, a single root, x minus 3. We can tell by looking at the factor that we're going to have an x-intercept at 3, and our graph should be cutting through that point. Here, we also have an x-intercept at +3, but since it's being squared, it will bounce at that point. Here, we still have an x-intercept at +3, but our graph, when it gets there, should flatten. Sketch the following. No, move on to the next side. When you have that information, move over to the next side, which I think is the last side of our notes for today. Okay, let's take a look at example G. This one is a little bit different from the ones we've seen up to this point. First of all, this one right here, that can be factored just a little bit more. That's a difference of perfect squares, which we've seen a lot this year. Okay. Now it's fully factored. Now we can begin graphing, or at least have an idea what this is going to look like. Let's start with our x-intercepts. We have an x-intercept here at positive 3. 1, 2, 3. Here, we have an x-intercept at negative 3, negative 1, negative 2, negative 3. Here, we have an x-intercept at 1. If you can plot your y-intercept, you want to do that. Also, let's look at our constants. Ooh, we have one there too. We haven't had one in front of our parentheses yet. So 2 times negative 3 times positive 3 times a negative 1 that we are cubing, which is still going to be negative 1. You multiply all that together, we're going to get positive 18. So our y-intercept is somewhere up here. Let's now think about in behavior. Now that this is fully factored, we're going to look at our factors here, here, and here and add the exponents. 3 plus 1 plus 1 is 5. This is a 5th degree polynomial. If you now multiply all the numbers in front of your factors, 2 times x times x times x is 2x cubed. It actually would be 2x to the 5th. Sorry, I'm forgetting that this one is actually x 3 times. So 2x to the 5th. Here's what we know. 5th degree polynomial, so opposite in behavior. Leading coefficient is positive, so we're going to end at positive infinity. So I'm going to go ahead and make a mark here and there. This x-intercept right here is the factor x plus 3. It has a multiplicity of 1, meaning my graph should go through that point. So that's what we're going to do. We're going to go through that point, through the y-intercept, and now we're going to approach our next x-intercept, which is going to be positive 1. Notice its multiplicity is being cubed. So when we approach 1, we're going to flatten, turn around, and when we go to that point there, positive 3, which by the way is this factor, since its multiplicity is 1, go through it. Here, I wanted to save ourselves some time, so I have given you an idea of what your answers could look like. Truly, you can come up with an infinite amount of answers, most likely. A quartic function with 3 real zeros and 2 x-intercept and a positive leading term could look something like this. We have 2 x-intercepts at negative 3 and 3. And notice they're bouncing because they're being squared there. If you want to copy the rest of this down, please do. If you have any questions over this, talk to me after notes. The last one that we need to end on here is 4 because they love throwing this stuff at you on tests. And these are pretty easy. I want you to get these. All right, I'm gonna start reading through this one. So for example 4, write a polynomial function of least degree in factored form that has the real zero shown in the graphs below and assume it's a leading coefficient of 1. So we're having to write what is the equation of this function. Let's identify the x-intercepts. Here, that x-intercept is negative 2. So as a factor, that's x plus 2. Then notice, what's your graph doing there? It's bouncing. And if it's bouncing, that means this factor must be squared. We have another x-intercept here at positive 2. So in factored form, that's x minus 2. It's also bouncing. Very good, sir. So then that factor must be squared. And then the last one. There's an x-intercept here at +4, so in factored form, it'd be x minus 4. It's cutting straight through, so no exponent. That's a lot. Take a photo of just this page right here. There's a lot of pages today. Submit them on my Canvas page. Get started on Delta Math. If you need any help on that Delta Math, come see me.